Hello, nice to be here. I'm waiting for my slides to show up, and let's see if the clicker works. Yeah. So, just to say a little bit why I'm here and why I usually do. My name is Erik. I work at Volvo Cars in Lund, and I'm working with software that's actually in the cars right now. I mean, there's so much happening in the car industry, but I usually work with software that's running in cars that are not in production yet. So you don't have to be afraid that anything that I've written will kill any of you yet. We'll see how that goes. Um, I have a background in mostly working with performance. That's really what I like doing. Done some rendering and photorealistic rendering. I used to work for Edgement as well. And apart from that, I also like to meditate and do mindfulness things and so on. But what I'm talking about here today is the car industry, automotive industry, and what has happened in the automotive. Can you press space? Let's see if it's. We'll see if how this works if the clicker continues. Yeah, how the automotive industry is changing. Because it's really like taking a giant leap, and lots of companies that are not so much software companies are becoming software companies, and it's really interesting to see this happening from the inside. But if we look in the rear mirror first, then I mean, there's been different computers in cars for a long time, and there are lots of sensors in a car. So when you look back, I mean, in the beginning, you just had sensors and you had just one computer in the car. And this is like in the 70s or something. And then in the beginning of the 80s, you started to have buses with data. And this is when the famous CAN bus that was introduced. And when I started in Volvo, I didn't know anything about cars. I mean, I'm not so interested in cars as such. I'm more interested in the software. But the CAN bus was something I know that there exists at least one CAN bus in the system. And that then was introduced in the beginning of the 80s. And basically it allows you to have multiple different small computers scattered all over the car to communicate with each other. And now let's see if I can. No. So let's I'll leave that one, and we'll do it like this instead. So this is a picture of the electrical system in a car. And you see there are lots of wires, first of all. There are like several kilometers of wire inside the car. And all of them connect to different sensors. I mean, you can get a feeling that there are lots of sensors, but you usually don't really think about it. I mean, you have, of course, lots of sensors in the engine itself, and like all of how that is automated and how that works. And the brakes have their sensors. There are sensors in the seat that you're sitting on, if you have seat belts on, and that become lots of sensors and lots of data. And now we're adding autonomous drive. So now it's not just someone is sitting on the seat, which is like just one bit of data. Now we're going to transfer lots of images and radar images and LiDAR sensor data, and all of that is going to traverse this car, and we're running out of bandwidth. And one of the reasons that also complicates this is that we're working with something that is safety related. So in the automotive industry, just to give some things here, we make a separation between what's safety and what is security. So safety is anything that goes with driver safety. The brakes need to work. That's a safety function. Security, on the other hand, that is hackers. We need to make sure that there's no malicious attempts that can break your car. I mean, that someone remotely can start the brakes while you're driving on the highway or something like that. So that's security. So what we're talking about here is safety first and foremost, and that's what I'll be talking about. And then you just add the security on top by having good architecture maybe adding some hash signatures or something like that. So, but for the safety part, the brakes need to work. The way that you solve this is that everyone in the system is always like saying, this is my value, this is my value. So if you're driving down the highway and your speedometer is like 100 kilometers an hour, then that is reported several, maybe 10, 15 milliseconds. That sensor is like just pumping out this data, because that's the only way that we on the other side can notice that, oh, we just lost communication with the speedometer and we need to slow down the car and stop it in a safe way. But since we have all of these sensors, there are lots of data going on in these buses. So we need to make some quite drastic changes to how the car is built. And when you have a car like this, so this is actually not the Volvo car, it's a Bentley, because that was the only nice image that I could find about how the electrical system works. But here it's separated on the different vehicle functions typically. So there's one group of guys working with brakes, and in this traditional architecture, they have their own CPUs. They're not called CPUs, it's called ECU, for electrical compute unit, just because in the automotive industry, we just want to have different names to everything. And then there's a VCU, which is also a CPU, but it's just a little bit larger. But then you have, so you have a group of people working, for instance, with brakes, and they have their own computers. And typically it doesn't even run a real operating system. It can be a microcontroller, maybe no memory controller at all. So you have full control of everything that is executing on that chipset. And that is how you also can make guarantees that if you're if you're doing multiple things at the same time, there's no, they don't interfere with each other. And therefore you have hundreds of ECU in a car. And each of them is just taking care of their small part. And then when they need to communicate with each other, they put the data on the CAN bus, and others that are interested in this information, they will pull it from the CAN bus and act on it. So if we go to the next slide. But since we don't have enough bandwidth on the cars, we're changing the whole architecture. So what we're moving towards now in the automotive industry is to have fewer CPUs, but with much higher compute power. Because I mean, somewhere now we need to do neural networks to make a self-driving car. You need to analyze camera frames, you need to analyze the radar images and so on. So we're combining all this data into fewer computers, and then you have more like, actually a little bit like a microservice architecture. We have lots of different applications that run inside that CPU, and we just aggregate all the data in there, do computations, and then we push the data out. But even having just one of these is not enough. So then, and we're a little bit in this shift right now where you have like one or two, and what the next architecture will be here, what you can see here is these zone controllers. So before we used to have the work was separated depending on the vehicle function. So brake for its own, speed on their own, and so on. And now it's more like, okay, so we have the right zone, right front zone. That's all the sensors in that area. They will talk to that compute cluster. And we have a couple of compute clusters in the car, from 1 to 4 in this case, depending on how much compute you need and depending on like if you have radar and lidar and all of that sensor data. And this makes it quite different in how we separate the different vehicle functions. Because now all of these are coexisting inside one or a few computers, and we need to make sure that they don't interfere with each other. And we need to know this on beforehand. Because like compared to when you have a cloud that you can push everything to, in this case, the hardware is set long before we actually get to building the software. And we don't know the applications that will be running. And the applications will be very heterogeneous. So, I mean, they will do completely different stuff. It's not the same service that's running just 100 times. It's completely different services that will load down the system in completely different ways. And what we want to find out is if we have enough performance so that we can actually run all this application code as early as possible. So that's like the problem that we're facing. And if we go forward, yeah, so this is like it. Before we had vehicle functions has their own microcomputers. Now we timeshare them, and we need to make sure that we still can run all of this, and what we then call that it's freedom from interference. That's part of the safety analysis of the whole system, that we can guarantee that the different parts don't affect each other. And go forward. And next one, and next one. So I'm going to start talking about micro benchmarks. So this is how we start to see a little bit about how much CPU that we actually use in a system. So micro benchmark is a little bit like a unit test. You have a really small piece of code, and you want to find out how much CPU power is this using, how fast is this piece of code. And of course, we have like the whole tree. So I mean, we're going to build this up now from the unit test level or the micro benchmark, and then you can do larger and larger benchmarks until you can see the whole system in some way. So with a micro benchmark, we measure a small piece of the code in isolation. It typically executes on an otherwise unloaded system, and we often focus on the best case performance. So this is really great. Like if you have some small piece of code, you want to compute something, you want to like either have an image detection for something and you want to compute that, or you have some other small computational unit that you want to find out how much CPU will this actually use. Next slide, please. And when we measure time, we have some factors that affect it. So what we really measured is the T on the left, the T measured time. And the T actual is what we are interested in. This is the time that the code actually took. But then we have some noise factors that combines when we try to take the time, when we try to time this code. So we have a quantization problem, which means that when you're measuring time, the clock that you're measuring is not continuous. So depending on the system, this could be like in the microsecond range or millisecond range. And this is like if you do a tight loop and you just measure the clock after each other, either you'll get 0 or you get some small number. So that is the quantization, is the minimum step that the system clock takes between two different values. Then we have an overhead. So I mean, if you do a tight loop and you just measure the time, how long time does that actually take? How long time does it take to measure the time? And depending on the system, this is not insignificant. I mean, and we need to compensate for that when we do our measurements. And then we have the system overhead as well. And the system overhead is like you get the context switch. You start running your system, your small program, and then while you're in the middle of that execution, the OS that you're running on decided, oh, I'm going to do something else. So it jumps to something else, does some work there, and then comes back and continues your benchmark at the end. And then suddenly we get these, since we're measuring the time, the system time, like the wall clock time, how long did it all this take? Suddenly we get some overhead from non-related parts, and we want to filter out that as well. And the way that we get around this is that we measure everything in a loop. So if I want to find out how long time does it take to do just one addition, like one CPU instruction, then you make a tight loop around that. And instead of measuring just one addition, you run it in a loop and you measure it. So first you try it one time and you get some number and you see that, okay, compared to the quantization that you first measure of the system clock, this is way too small. I get 0. It didn't take any time at all. And we know that that is not correct. So then we try it 2 times, 4 times, maybe we try it several thousand times before we get a measure that we actually, a time measurement that we actually can use. And if we go to the next slide. And we shouldn't need to really care about this ourselves. So there are several good frameworks for doing this. I usually work in C++, so I use Google Benchmark or Facebook Foley, where all of this is already encompassed in the system. But I mention it here because I've seen so many cases where people try to measure and they don't iterate the code that they want to measure. And they get numbers that they try to draw conclusions from, and the numbers doesn't say anything. There's no correlation between the numbers that they're looking at and actual code, how fast it's executing. So we need to have a benchmarking system that gives us reliable numbers. Next slide. And this is nice. This allows us to measure small pieces of code. But there are some things that it doesn't measure really good. Impact of cache misses or communication. So whenever we do communication between different applications, and I'm saying on the system we have multiple, I call them applications. They're like the car and the brake system and so on. And they talk to each other. And when we need to measure that, then we need to do context switches in some way to go from one process to another process and then come back again. And they are hard to measure in a tight loop, especially if you just have one-way communication. You have code that sends data from one point to another point, and it's hard to measure that in a tight loop. And since we're doing a tight loop, the cache misses will not be part of this because we will execute in the same memory areas over and over again. So the cache will be warm. And sometimes this has a really big impact. So because the code that we execute, I mean, take for instance how the engine is controlled. So we have we know how fast the current car is driving, and there are lots of inputs to this system, and it's typically modeled in Simulink, which is a MATLAB thingy, if you know that. But it's basically a mathematical model for how the engine should be controlled, and all of that is then the tool generates code from that. So it's generated code that executes. And the amount of data that it uses is not that much. But it's executing at a timed interval. So maybe it's executing once every 10 milliseconds, or once every 15 milliseconds, or 20 milliseconds. But 10 milliseconds, that is so far away that the cache can have gone cold in between the different invocations. So by locating the data in a better way, so that you don't get as much cache misses per iteration, you can get lots of performance impact. Because, I mean, if you look back in the day, everyone used to talk about the square root. I mean, if you wanted to have something that took really long time to execute, everyone talked about square root. That is really slow to execute. But it's not that expensive anymore. So, I mean, a square root is really optimized, and it's only CPU instructions. And a cache miss, so doing a square root can take maybe, let's say, 10 nanoseconds or something. But doing a cache miss can take 150 nanoseconds. And that is for the level 1 or L0 cache miss. And then as you go down the cache tree, the cache misses become more and more expensive. So optimizing for cache misses is like really the bread and butter to get a really nice performance system. Next slide. So to get some idea of how we can measure the cache misses, we can use different performance counters. There are two ways. Either we can use emulated performance counters. For instance, if you use Valgrind as a tool, then you can emulate the whole CPU and you can specify this is how much cache I have, and it counts whenever you do memory accesses that would produce a cache miss. Or you can use hardware counters. So if you're on Linux, there's a really nice tool called perf that talks to the performance subsystem in the Linux kernel. And that allows you to see the CPU view of how many cache misses that you have, for instance. So here I'm running perfstat, and I say that I want to get these cache references, cache misses, number of cycles, instructions, and so on. And I run my benchmark. Next slide. And we get these numbers back. So this is how you can run your micro benchmark and see like how well did this do from a cache point of view, or how many times that you had a page fault and all of these things. So that's really nice way to get some more numbers than just the pure performance numbers. And then using this, you can sort of force your benchmark to be in a state where it triggers the same cache misses that you would do in a live system. Next slide. But that is all theoretical, or sorry, that's all the practical part of the micro benchmarks. But we can also do a theoretical view of this. So if we look on the next slide, there's something called the roofline model. And the roofline model, it's a way to look at how an algorithm uses computational resources and memory bandwidth. Because these two are usually the most limiting factors when you have a tight problem that you want to solve. And if we go to next slide. So for a system, it basically looks like this. Now, I don't have any units on this, so it will be different for different systems. But down here on the right, or from left to right, we have the arithmetic intensity in instructions per byte. So this is how much memory access do we do per computational unit that we use. And on the y-axis, we have the attainable instructions per second. So that is like how many instructions that we actually can execute. And all problems that we have will be somewhere down in this graph below the red line. And when we get to the red line, we become limited either by the memory bandwidth, and that is if we go in the slope, or if we run into the top, then we have peak instructions per second. So we're bound by the amount of CPU crunching that we can do, basically, like how many computations that we can do. And this gives us an idea of what kind of optimizations that we can do. So if we're on the memory bandwidth bytes line and we're close to that line, we might get better performance. We want to go up as high as possible. And then we might be able to switch from doing computation to load that data from memory instead. But it depends on your actual system where you are. Next slide. And in reality, there are multiple roofs. So I mean, it's called a roofline because it basically looks like a roof. And depending on whether your data is in cache or not, you will have different memory bandwidth. So there are actually several ceilings here that you can run into. And if you can shrink your program so it fits in L0 cache, then it will be much faster than if you need data. So that comes from the L1 cache and so on. So that's the theoretical part of this. And if we move on, so can we use the micro benchmark to see how the whole system will behave? Next slide. And sadly not, because we want to also be able to run the whole system to know that the code that we're optimizing or the code that we're measuring is actually relevant. I mean, if the code that we're optimizing is never executed, then it won't affect the final performance. So to get the final performance, we really want to do a full system profiling and see what is the code over the whole system executing, so that we know which parts of the system that is relevant. Next slide. But profiling requires that we have a running system. And as I said in the beginning, we don't have a running system yet. This is like way before the software is actually developed. And next slide. So what I've introduced and looked at is something called benchmark sensitivity. Next slide. So when we try to do something that's really fast, we have some basic goals. We don't want to use dynamic memory. We don't want to use system calls, because all of these things are things that take really long time compared to like doing CPU crunching. But sometimes we don't have any way around them. I mean, if we want to communicate between two different applications, the system needs to be involved in some way. Next slide. And then we can find out that when we do the next level of performance checks, then we're not limited. It's different kinds of limitations. So as soon as we start talking between different processes, it could be other like mutex locks within the kernel that limits us, or some other VM thingy that is the actual limitation that lowers our performance. And if we just run the micro benchmark or a small module benchmark on this, then we don't see the actual problem because the system is not loaded yet. Next slide. So that's why we want to introduce some stress testing as well. So we want to put stress on the system while we're running the benchmarks. And then we want to see whether we get the same benchmark values when the system is in stress and when it's not in stress. And if the system is in stress, if there's a really big difference, then we know that this piece of the code is sensitive to this factor. So if we go to the next slide. So stress-ng, that's a Linux version of this, and there are others for different operating systems. And it can load down the system. It can do different system calls and do them in a tight loop in different ways to try to fill up the CPU or the memory bandwidth. There are like stressors that just tries to load as much as possible from memory so that we fill up the memory buses. We can have VM stress so that it tries to switch, like running different Docker images, or if you're running multiple virtual machines. Will that change the performance? And next slide. So if we run this micro benchmark on one core and we run the CPU load on another core or normal benchmark, and we get the same benchmark values, then we know that we're insensitive. But if they're changed a lot, then we know that this parameter is something that we need to take in consideration when we look at this system. So if, for instance, if we want to look at communication between two different apps, we have a small benchmark for that piece of the code. And we start at the same time, we run lots of memory intensive things on all the other cores. Then we know that we will not be able to combine applications that have a lot of CPU work at the same time as we do the communication, because that will like drag down the whole communication stack at the same time. Next slide. Yeah, and if we get the same performance, then the test is insensitive, which is a really good thing in this case, because then we know that we don't have to think about this factor ahead of time. We can just let these different loads run at the same time, and they will not affect each other. So final slide here. Be aware of how to interpret the data. And this is like this. These are things that after you've been looking at these numbers for quite some time, you start to see patterns. So more data stalls can be good. I mean, it can be good if you have one, you start with one algorithm and you try that out, or one implementation of your algorithm, and then you do next implementation that you think is faster. And if the new algorithm actually is faster in wall clock time, but from the counters, it looks like we have more data stalls, then that can be good, because that algorithm or that implementation is then limited by the available memory bandwidth. And lower CPU usage can be bad if the application is blocked on I/O. So one of the problems that we had in the beginning in the project that I'm on now was that the logging framework was blocking the applications. So we had lower CPU usage because all the applications tried to use the log daemon, and the log daemon didn't have enough compute power to actually store all of these logs. So it looked like we didn't use that much CPU usage, but in actual we had more work that we wanted to do, but it didn't show up in our profiles because it was just one daemon that was the bottleneck of all of these logs, and that slowed down the whole system. And also that we can do more work at the same time if we use different kinds of CPU compute units. So in a modern CPU, you have different units that do integer operations and floating point operations, for instance. So if you have something that's really floating point heavy, then you can at the same time just add more integer math into the whole algorithm without actually affecting the end performance, because actually parts of your CPU is not utilized. So that's a way that you can try to make some of your algorithms, move them from floating point to integer, and suddenly things go faster, or you can add extra work at the same time without affecting the final performance. And also the final here, socket layout. So you will also often see that the different compute cores, the different cores inside the CPU, if they have shared L0 or L1 cache, you can see that the communication between them is different, has different speeds. So if you want to communicate between two different applications, depending on which CPUs that are currently running on, they will take different amount of time. So that's also a way that you can balance up the system by co-locating things to the same CPU core. Next slide. And the pitfalls: not measuring at all, then you don't know what you're doing at all. And if you're not measuring, then you can't optimize, because guesses about where to optimize will always be wrong. Measuring debug builds doesn't work. Measuring non-working code, that's really like, it's quite often you're doing something, it doesn't really work yet, but you want to see the numbers. But until your new implementation actually works, you can't rely on those numbers at all. And not having something to compare to. You always need to have something to compare to know whether you're good or bad, because you don't really know what you're comparing to otherwise. That was my final slide.